Reading through this question, we can see that this situation follows a normal distribution, and therefore our first thing to do would be to set up the standard normal distribution curve and enter the mean, which is given to us in the information, and just write the standard deviation perhaps next to it, and just check the units that are in the same units here. Okay, so now we can go forward with actually answering the question. So what is the probability that a newborn baby in this hospital chosen at random weighs between 3.55 and 4.18? So 4.18 is above 3.55, the mean, and so we're looking at between, chosen at random weighs between, so shade in the between. Okay, so that now demonstrates what we're trying to find. You could write that down as a probability statement that you're looking for the values of x between 3.55 and 4.18. That's not necessary that you have this step here. It just is mathematical communication. Okay, so what we want to do now is, so this is currently normally distributed, but what we need to do is standardize it. So standardizing it means we need to we need to calculate the z value, so we can then use the standard normal distribution table to work out the probabilities. So our z value is found by using the formula given on your formula sheet, where we're looking at x is the mean, the x value is the value that we're looking at, so in this case it's 418, so z equals 4.18 minus mu, the mean, 3.55, and our standard deviation of 0.3. So enter that into a calculator and we should get a z value of 2.1. Now looking up, at this point we look up 2.1, the value of 2.1 on our z tables, and just to give you a quick rundown on that one. So the column down here, you're looking for 2, and then across to 1. So that value in there from our z table, our standard normal distribution tables, gives us the probability, as you'll see on the diagram, between the mean, standardized mean will be 0, and the z value, so that shaded area there. And so when you look that up, you get a z value of, a probability of, so the answer to this probability statement, a probability of 0.4821. Okay, so for this one is an achieved question, so we're just looking at a u at this point here. So we've got the same distribution that we were talking about in part 1, so where we've got a mean of 3.55 and a standard deviation of 0.3. And now we're going to answer the question, for what percentage of newborn babies would the hospital expect more than 4.0? So 4 is above 3.55, so more than is shading above it. Now I just want to remind you of the tables that we used just before. At the top of it, the standardized distribution, let me just tidy that up a little bit. Standardized distribution has a mean of 0, and our z value, the table calculates the value in here. So we need to recognize that both of those values, inside and outside the z on either side, are going to total to half, because that's exactly halfway. We know this distribution is symmetrical, so half above, half below, so half will be 0.5. So what we need to now do is work out our z value as we did before. So our z value is the x value minus the mean divided by the standard deviation. In this case we have a z value of 1.5. And so when we look at 1.5 on the tables, our probability is going to be, so the probability that, first of all, that x is between 0 and, what's that value, 4, will be, when we look up on the tables, just have a look, 0.4332. And so the probability that we're actually trying to find is where x is greater than, I'll just write it on the side, where x is greater than 4. And so that will be 0.5 minus that probability that we just worked out, because I just want to remind you that that probability is sitting in here. And so our value is 0.0668. Now, one thing just to be careful of here is that we need to go back to the question and see that it actually asked us for the percentage. So we must write this as a percentage, and that's 6.7 rounded to 1 decimal place. So just a couple of things to note. If you don't have the probability statements, these P statements here, don't be too bothered. It's mathematical communication, but you're not going to be marked down if you don't write it like that. It is more important, it's most important that you do your diagram so you're calculating the right values. Otherwise it's really easy to mess that up. And the last thing is, read the question and ensure that you are writing it as the question intended, as a percentage in this case. Do not be too worried about rounding. However, please try not to round too early. So any rounding, if you rounded at this point here, it would definitely affect your next value, which would of course affect your percentage. If you round too harshly, it can affect things quite a bit. So try not to round until the last stage if you have to. Alright, so this is an achieved question, so you must have the percentage written as percentage of 6.7 for the achieved. Alright, so we've got the situation as per before, where we've got a normal distribution with mean of 3.55 and standard deviation of 0.3, and we are actually asked in this case to look at babies less than 3 kgs and work out the expected number that are going to be less than 3 kgs. So identifying that on our curve first, shading in below 3, so less than 3, and just recognizing from our Z table that our standard normal distribution is actually looking at between 0 and Z, the shaded bit in here. So we need to make sure that we are, first of all, recognizing the symmetry, so whatever we want to calculate on the left hand side, but it will be the same for the right hand side. When we look this up in the table, it's going to be the shaded bit as identified in the diagram, and we're actually looking for this piece out here, so we need to take 0.5 away from that probability that we look up for that Z value. Okay, so those are the things we're going to do now. So let's get started. Z equals, so this is the formula on your formula sheet, and the x value in this case is 3, the mean is 3.55, and the standard deviation is 0.3. So when you put that into a calculator, you should get negative 1.833. It's 33 reoccurring. However, I'll work to 3 decimal places because the tables, the standard normal distribution tables, they go to 3 decimal places. If you were to do it to 2, that would be fine as well. Alright, so first of all, recognizing that the negative tells us it's on the left hand side, but it's the same as the left hand side, as I said before. It's the same as the right hand side, so we can actually use the value 1.83 and look that up on our tables. And when we do that, we can see that the probability that we are looking at is, the probability for that Z value is 0.4666. Alright, and the last bit of this sort of piece is that we are looking for, I'm just going to write this in full now, we're looking for the probability that x is between, sorry, rather, that x is greater than, that x is less than 3. So the probability that x is less than 3 will be, so we get rid of some of these arrows here, and I'll indicate that on our diagram now. So less than 3 with our shaded area here, 0.5 minus the probability of the inside piece. That works out to be 0.0334. And the last piece that we need to make sure we're answering the question is that we are given the value of 154 babies, and we're asked how many of those are expected to be less than 3 kgs. So 154 times our probability of 0.0334 that we just calculated, that gives us a value of something like 5.14. Okay, so we wouldn't normally say 5.14 babies. We would normally say either 5 babies in this case, or 6. Now, if you had the answer 6, you would be fine. That's fine as well, because you may recognise this as being, well, 5 will not quite give us that probability, so we'd need to have one more baby to give us that probability. So either interpretation of that answer would be fine, 5 or 6. Okay, so just letting you know where the marks actually sit for this one. So it is a full merit question when done completely. If you calculated the probability, and so that's to this level here, that isn't achieved. And if you calculated the expected value, the expected number in context, so rounding I would expect to be required here, will be your merit grade. So for this situation, as before, we've got our normal distribution rather, and our mean of 3.55, our standard deviation of 0.3, and the question is asking us what birth weight is exceeded by 20% of the newborn babies. Alright, so setting up that situation, we first need to recognise that our exceeded by is this bit in here, greater than whatever value that is. That's what we need to figure out, and that percentage is 20%. And if you recall from before, I'll just do this nice and fast. Our standard normal distribution is between 0 and z is the area inside there, and so we are going to need to look at this area in here, which is 0.3, 30%. Okay, so using our formula that we have so far, we know some of this information and don't know others. So let's just put in the information we know. We don't know the x value, that's what we need to figure out. We don't know the z value just yet, but we can actually find that from our tables, and I'll show you that in a second. And we know our mean is 3.55, and we know our standard distribution. So we need to figure out our z value. We do that by looking up, so if you recall, this is the area inside is the probability, so that will be 0.3 that we're looking up on our tables to find our z value. So when we look up 0.3 on our, so this is the bit inside, so if I just set up a little z table here, it's the value inside here as close to 0.3 as possible. So when I look up 0.3, as I'm doing right now, I can see that 0.2996 is very close to, the next value above it is above 0.3, so it's 0.3023. So I really want to work with this one, and that one currently is 0.84. Now I know that I'm still a little way off, and I can add a decimal point of 1 and get a value of 0.2999, which is extremely close to 0.3. So that's the z value I'm going to work with. Okay, so let me put that in here now. 0.841. At this point, calculate your x value. I'll just actually write this times 0.3, and that will give you x minus 3.55, and the x, then add whatever you get there onto 3.55. So all I've done is, with some basic algebra, rearrange the equation to work out the x value. And the x value, if I go to my answer schedule now, is going to be, actually I don't know that one, just give me a moment. 0.841 times 0.3 plus 3.55. So it should be an x value of 3.8023. I do have that rounded to, in this case, well, you can leave it just as it is, or you can round it to 3.80 is what the answer schedule is actually rounded it to 2 decimal places, but I'm perfectly happy with 4 decimal places. It's absolutely fine. Okay, so where the marks sit with this one, we have got, it's a merit question in total, the inverse normal value of z found, so actually calculating your z value at this point here, so that's achieved. So that might be shown there, or it might be shown in your calculations over here. Now, the full calculation following through to the x, to calculating the x value, is a merit. This question is so still looking at the same situation with our mean and our standard deviation. This question is looking at what is the range for the central 80%. So central 80%, if I just set that situation up, is right in the middle with 3.55. So it's either side the central 80%. So this, all of this area here is 80%. Oops, or 0.8 if you like. Therefore, each of the halves of that 80% is 40%, or 0.4. So we know the area that we're dealing with is 0.4. We don't know this value here yet. That's what we're going to figure out in this value here. So we're actually looking for the range. What is the range of central 80%? So we're looking for the range, or the space between those two, the difference between those two values. Okay, so let's just work through this to figure out, I actually change colours there, let's figure out this x value for where 40% is between the x value and the mean of 3.55. So as we did before, our z calculation formula, and substitute in the values that we know. So we don't know the x value yet, we know the mean is 3.55, standard deviation is 0.3, and we can look up this z value by recognizing we want the area under the distribution curve to be 0.4, or the probability 0.4. So when we look up 0.4 in our formula tables, on our standard distribution tables, we get a value of 1.281, and that's to 3 decimal places, but feel free to do it to 1 decimal place if that's where you go with that. 1.281, and from this point we are, as we did before, we are calculating the x value by using some basic algebra and I'll just write down actually what we're doing. I'll put the x value on this side. We are rearranging this so that we can figure out that value that we are looking at for x. Okay, so when you do that, that's a 1 there, sorry. When you do that, you get an x calculation of 3.9343. So that's just telling us, I'll redraw that again. You don't need to draw it this many times, just draw it so that you can see what you're actually doing. So this value here is 3.9343 to 4 decimal places. That's the value there. Now the difference between those two, sorry, try to change colours here. The difference between those two is 0.3843. Recognizing that that is the same on the other side because it's symmetrical, so we're going to multiply that by 2 and you'll get a value of, let me see, what do we get? 0.7686. And that's the final answer. So our range, so the gap, if you like, between those two is 0.7686. I noticed the answer schedule rounded it to 0.77, and that's perfectly fine. There's no worries at all. Whichever answer you put, try and put the context that you're dealing with. So in this case, we're talking about the kg. So a variation of 0.7686 kgs for the mid 80%. Our grades are given as the inverse normal value of z is found. So that's this value here. That's for your achieved mark. The x value calculated, and that's for your merit mark. Applying it to the range, so specifying the range, that's your excellence mark. So we've got a graph drawn for us, and we're just basically asked to interpret the information from the graph. So we're given the frequency up the side, the vertical axis, and the baby's weight along the horizontal. So in this case, we're asked what proportion of babies weigh less than 1.75 kgs. So our weight is along the bottom, so weigh less than 1.75. So that would be, there's 1.5 and there's 2. So that would be less than 1.75. It would be this range below here. And you can see we've got none in this bar here, but we've got 1 sitting in this bar here. Now 1 means, so the frequency means the number of times this occurred. So I'll just write that down. So frequency is the number of times that weight occurred, the weight for that bar. And so we've got 1 baby was below 1.75, so we know we're dealing with 1 out of how many in total, how many babies were born in total. So we'd need to add up these frequencies. So 1 baby was there, and so this is 2 babies for this bar, so that's 3 babies in total so far. And then we've got 4 babies who were 2.5, so that's, what do we say, 1, 3, 4 is 7, and then add another 8 on, 15, add another 9 on, what do we get to 24, add another 7 on, 31, 36, 39, 40. So there are 40 babies in total that were born from this data. So the probability of being less than 1.75 is 1/40. Now that question is an achieved question. We're asked in this question whether Gina is justified in thinking that this is a normal distribution. So we need to think about what makes a distribution normal, and I'll try and do that a little bit better than that, sorry. And what makes a normal distribution normal is that the data is evenly spread around the mean. So this side and this side are the same, or pretty much the same, so it's symmetrical. And sorry, I've spelled that wrong. Symmetrical, looks right. It's symmetrical around the mean, and the tail ends are very small, and the mass of the data is in the middle. It only has one hump in it, if you like, not two, so it's not that kind. So that's called unimodal rather than bimodal. Modal. What else are we looking for? Yeah, so that's pretty much it actually. So looking at this data here, then we can see that for this data it is essentially bell-shaped. Okay, I know there's a little bit of a gap in here, but essentially, and it's not exactly the same on this side and that side. There's a little bit of difference there, but essentially it is. So it is approximating a bell shape. It is unimodal. Spell that right this time. We only have a small number of values or occurrences at either end, at the ends. So therefore we can say that it is, I'd like to say that it is symmetrical around the mean. So we can say that Gina is justified in thinking that the distribution is, so I'd make some sort of statement to that effect. Gina is correct. In saying the weights are, I'll change that to weights are normally distributed. Try and put the context correctly in there. It helps for your application of the question. So what have we got here? The answer schedule says a correct and relevant statement. So one correct and relevant statement, complete explanation given for merit. So looks like we could say one of these for achieved and two of these or more of them for merit. You don't necessarily need to have all of them there, but obviously be as thorough as you can, please. Okay, in this question we're asked to compare the distributions of these two graphs for the data given. So we've got Gina's study for the ones in hospital, and as we said before, that essentially is a normal distribution because essentially they were symmetrical about the mean. It was unimodal, and only a few of the data were at either end. Now, when we look at the birth of the babies born overseas, we can see that it's doesn't fit nice and neatly to a bell shape. There's quite a big gap in the middle here, and there's quite a bit of data on those bits there that sort of are outside the bell shape, and they're quite big clumpy bits. So in fact, really, we could sort of say that this is, two clumpy bits there, so that's called bimodal. As the other one was unimodal, this one is bimodal. Even though the ends are a small number at the ends there, really looking at the ends in that sense, they're not small values at either end, they're quite big numbers there. It's actually hard to see where the mean is, but if we sort of took the mid-range mean as being here, it's not symmetrical. It's not symmetrical around the mean. We've got more values up here in that group and here in that group. Okay, let me get rid of all these circles and actually start making some statements. So just thinking it through and just comparing the two is the first step with this, and then you can start making some statements. Try and be statistical in your statements, but even if it's just in what you observe, you're better to do that than leave it out because you don't know the correct stats words. So we could say that it is not, the overseas babies are not normally distributed. And we want to make statements as to why. So why? Because is bimodal with two clumpy bits, two clusters, just saying what the answer schedule actually says. Clumps in the answer schedule. Doesn't really matter how you describe them as two larger proportions rather than one. One clump, if you like, in the hospital ones. Okay, the other fact is it's not centrally, so the data is not central around the mean. To the mean, it's basically skewed more to the left side. Skewed to left. Okay, so it's sort of shifted over, if you like. What else are we saying? The spread. Oops. Is not close to the mean. So therefore it must have a higher or larger standard deviations. Away from the mean. So it just means it's spread out a lot more. So if you were to break this into standard deviations, you've got, you know, larger standard deviations rather than this one's quite close to the mean. Okay, checking to see if there's anything else we could be saying here. Yeah, that pretty much says it. So not central, two clumps, so bimodal. Perhaps we could say that the data at the ends, so the data at the ends are quite large, especially at this end down here, the left end, much higher, much larger. So not petering off, not getting smaller at the ends. Okay, I'll wrap this up now. So we are looking at, for achieved, a statement and a correct reason. So one of them for achieved, statement and incomplete justification. So maybe part of this, you're part of the way there. So maybe just say 2 points but not justifying it completely, so not fully explaining why. So it could still go either way if you like. A full justification, so pretty much all of these statements would be good for an excellence. So what proportion of people surveyed is obese? We're looking at the information in the table above, and we're answering the questions for each situation from the table. So the proportion of people, proportion is just looking at probability. So for example, a proportion is a fraction, a decimal, or a percentage, and probability can be expressed as a fraction, a decimal, or a percentage. So you'll often find different words for probability meaning the same thing. So what proportion of people? It's just looking at the probability. So the probability of the people surveyed, all the people surveyed that are obese, so all of the people surveyed is 290, the number obese is 75. So 75 out of 290 is the correct answer. You can write that as a decimal as well, but and you can also, if appropriate, you could simplify that fraction, but it's probably best just to leave it as it is, then you're not going to make any mistakes with it if you don't need to. The second part of this question is asking for a percentage. You do need to give the answer as a percentage. So the people who are regular energy drinkers that are obese, so the regular energy drinkers that are obese is 56 out of 148. So 56 out of 148. We are asked to give this as a percentage. So just pop that into your calculator and multiply by 100, and that's going to be 37.8%. You can round that appropriately. So you could round that to 38%. Possibly you'd get away with 37%, although that's not really appropriate in this case. Okay, so we've got the first part is an achieved question. The second part is a merit question. So part 3 is asking us what proportion of the people in the survey were not obese and did not use energy drinks. So not obese and did not use energy drinks. So not obese, so this column here, and not energy drinks, this column here. So 123 matches both of those criteria. So 123 out of the total people treated is 290. And part 4, now you can leave it as a fraction or you can make it a decimal. Part 4, if a study of U12 students necessarily carried out with 1,500 participants, how many would we expect to be regular energy drinkers? So regular energy drinkers is this one here. So we would expect 148 out of the 290. So 148 out of 290, and then multiply that by the number of people that we are looking at, in total. And so the proportion of that number of people would be 148. 148 divided by 290 times the number of people we actually surveyed or looked at, and so that would be 765.5. So you can, as this answer, round it to 766. The answer of 767 was also accepted for this one. For what reasons, I'm not quite sure. And I guess it would depend on your rounding. If you happen to round this one here, then that would make a difference. All right, so that is going to be a merit. And sorry, this one up here is going to be an achieved. Okay, so for this question, we're asked to justify this statement of comparing two probabilities. So this is actually looking at the relative risk of one thing occurring in relation to another. So we're looking at the probability of one event in relation to the probability of another event. So we're actually told that this newspaper has said that it is 3 times more likely. So they are saying that this answer would be 3. And so the probabilities that we're looking at here, newspaper states that regular energy drinkers, so regular energy drinkers, are 3 times more likely to be obese. So regular energy drinkers that are obese, if you like, than if they were not regular energy drinkers, so not regular energy drinkers who are obese. So we need to look at these two probabilities. So the probability of being a regular, I'll just write it a little bit fuller now, regular energy drinker and obese. So a regular energy drinker and obese, 56 out of 148. And the probability of not a regular energy drinker and being obese. So that probability is going to be, choose green colour, not regular energy drinker and obese, 19 out of the 142. So comparing those two probabilities, we're just going to divide them. I'll just actually put a line here so you can see. I'm actually just taking the top probability, dividing it by the second one. Now, when you do that, you get, I'm just going straight from the answer schedule here, an answer of 2.82. So your answer may be slightly different depending on how you rounded, or if you rounded. If you didn't round, it's actually it's really good if you don't round and you just put the two fractions divided by each other. And you can see this probability is fairly close to 3. So you could then justify the statement and said yes. So yes, the newspaper article is correct. Is correct in saying 3 times in stating this as the relative risk, and you might actually just use a few more words here, the relative risk of, and make the statement of what you're comparing is 2.82, which is close to 3. Indicating 3 times is indicating the first outcome is 3 times as likely to happen as the second. I mean, I'm being pretty thorough in the answer here. You probably don't need to state quite this to this depth. I'll just go dot, dot, dot. You can carry on with that. So the first outcome is 3 times more likely to happen than the second outcome. And marking for this, if you comparison made of a non-obese, so if you actually had the two probabilities compared here, that would be your merit, and if you justified that or related it to what the newspaper article was saying, interpreted what the 2.82 or the 3 actually means, that's your excellence. Part B is building on the information from Part A. So it's still using the 290 students we were looking at in Part A, and we're saying that 60% of them did regular exercise. So of the 290, 60% of them regularly exercised. So that's 174 students. And of that 174 students who regularly exercised, 1/6 of them were obese. So that gives us 29 students who were obese. So we can use this information to start completing the table. So we've got a total number of students of 290, 174 of them regularly exercised, and 29 of those regular exercises were obese. Therefore, 145 were not obese, and 116 did not do regular exercise. Now recall from Part A, it is the same students we're looking at, so we know that of those students, 75 of them were obese. So our total here is 75. Therefore, 46 were not regular exercises. And so the not obese students out of the 290 were 215. Therefore, 70 were not regular exercises of the not obese. Okay, so then answering the question that's asked, what is the probability that a person in the survey who is not a regular exerciser, so someone who is not a regular exerciser, is not obese? So not obese, not regular exerciser. So 70 out of the 116 who were not regular exercisers. So this gives us a merit answer in total. If you completed the table but did not do the probability, you would get achieved. In the second part of this part B, we're told some researchers claim that relative risk of a regular exerciser being obese is less than half as likely as the person who does not exercise regularly. So a regular exerciser being obese is less than half of the person who does not regularly exercise being obese. So we need to justify that as being correct or incorrect. So what we're actually looking for here is a relative risk. So that's the probability of one situation in relation to the probability of the other. So the first probability, what we're working out here, is the probability of a regular exerciser being obese. So a regular exerciser being obese. So we're looking at the information from part B that we just worked out before. Regular exerciser being obese is 29 out of the 174. 29 out of 174. And that's going to be divided by the probability, if I just write this down below it, of the person is not a regular exerciser. So a non-regular exerciser being obese is 46. So not a regular exerciser being obese, 46 out of the total who are not regular exercisers of 116. Okay, so the relative risk, I'll just call it RR, is going to be 29 out of 174 divided by, like that, 46 out of 116. Pop that into your calculator without rounding if you can, but if you round, you're just going to have a little bit of variation in your answer. So the answer comes to 0.42. Now the question has actually, if we go back to the question, it's actually asking us is this, so saying that the regular exerciser is less than half as likely to be obese as the person who does not regularly exercise, is less than half as likely. So this tells us, 0.42 tells us that the relative risk of the regular exerciser being obese is 0.42 in relation to, or 0.42 times as likely to be the case for this probability as for a non-regular exerciser being obese. So the claim is actually correct. So we need to make that statement. So relative risk of the exerciser, regular exerciser, being obese is 0.42 times as likely I'll just times more likely or less likely. I should change it to less likely to occur as a non-regular exerciser. So the claim is correct. I know I've taken a long time to write this statement out, but you do need to make sure you're interpreting what you're calculating. So interpret what your calculation actually means and make the statement as to whether it is correct or incorrect. So you must justify whether you and on the claim, so rejecting it or accepting it. So the marks for this in total, if you had to that point, is an excellence. If you compared both probabilities, so you would need to calculate these probabilities and make some comparison. Maybe probably at this point here, because you do need to make the comparison there, is merit, and actually calculating the two probabilities but not comparing them is achieved. Question 3 on probability trees is, so when we read through this information in the intro, we can see that we've got 88% of the group have their driver's license for more than 5 years. So that's this probability indicated on the tree here. And the alternative to having the driver's license for more than 5 years is having it for 5 years or less. So it can only be one of those two options. So that must be 0.12, i.e. those two probabilities must add to 1. And that is what the question is asking. So what is the probability of having driver's license for less than 5 years or less? Must be 0.12. And that question is a fairly easy achieved question, on the easier side for sure. In part B, we're told a little bit more information to add to our tree. So we're told in the group that had their license for more than 5 years, so only going on this side of it, 38% passed both the tests. So passed both tests is this piece in here. So 38% is that branch there, and 40% passed the practical tests only. So 40% is that branch there. And then it says half of the rest of the group passed the theory test. Alright, okay, so we've got two more options left. So we're saying half of them passed the theory test. So we know that this, whatever's left over, is split in two. We also know that these are the total number of possibilities. So those possibilities all need to add to 1. All of those probabilities need to add to 1. So for the branch left over, the two branches left over, we have 1 minus the 0.78. That's those two probabilities added together. So that leaves us with 22% or 0.22 split between those two branches. And we're told that half of them had passed the theory test. So therefore, each of them is going to be 0.11 or 11%. The question then asks, what is the probability that a randomly selected person in the survey had their license for over 5 years and failed both tests? Just take away some of this stuff here. So we're looking at the branch that had their license for over 5 years and failed both tests. Both years, had it for over 5 years and failed both tests is this branch down here. So we've got a probability of 0.88 times 0.11. And that gives us a total probability of 0.0968. And that's the answer. So that's a achieved grade. Alright, the next part of this is looking at, in this case, the group that had their license for 5 years or less, and we're told that all passed at least one test. So looking at this branch and passed at least one test. So you'll see that there are only 3 branches off here because we don't have a failed both tests. And we're told that 52% passed both tests. So 52% passed both tests is 0.52 on that branch. And 30% passed the theory test alone. So 30% passed the theory test alone. So that's down here. And by the way, remember from over here, this is going to be 0.12. And so, as I said before, when we have total number of outcomes, we know that these have to add to 1. So our branch left over is going to be 1 minus 0.82. And our question is asking, what is the probability that a person selected at random from the survey had their license for 5 years or less, and passed the practical test alone. Practical test alone. So therefore it is 0.12 times 0.18, which gives us 0.0216. The second part of this question is asking us if this group was a typical of 3.2 million drivers, so in total population, how many drivers would pass both the practical and theory driving tests? So pass both the practical and theory driving tests. So this is of both groups, had their driver's license for more than 5 years and had their driver's license for less than 5 years. So I'm just going to change my colors here, and I'm looking at driver's license for more than 5 years and passed both tests. Passed all tests, so passed both tests is that one there. And remember from before, that's going to be 0.88 times, from our previous question, we know that that's 0.38. 0.38. And we also need to look at the group that had their license for less than 5 years, this group down here, and passed both tests, so this branch in here. So that's now looking at adding in the probability for the less than 5 years, 5 years or less, and pass both tests. So work out both those probabilities and add them together, and we should get 0.3968. We're not complete yet because we still need to work out how many of the 3.2 million will have passed both. So 3.2 million people times, so 3.2 million, it's probably easier if we write this as the number 3.2 million, 3,200,000 times our probability we just worked out. Pop that into a calculator and you get that number. So where are we looking for our marks? This is a total of, in the first question, achieved, and in the second question, a total of merit if you had it complete. However, if you had just the probability, that would be an achieved question. Right, part C one is actually referring to the information in part 2 as well. So if I just refer back to that information that we did just before, we know we had passing both tests and passing both tests for the other one is, just let me just, had their driver's license is 0.12. Passing both tests is 0.52. From our previous question, I'm just checking that I had that right. I did. Okay, and so we're told that from those people that passed both tests and had their driver's license for 5 years, 56% were female. So of these, we're either going to be female or not female. So 56% are female, 0.56 there. And of those that passed both tests and had the driver's license less than 5 years, again, they're either female or male, and that would be 41% female. So what is the probability that a person selected at random from the survey is found to have passed both tests and is female? So we're looking at the two probabilities in total, combined, added together. And just pop that into a calculator. 0.41. Add them together and you should get, and that's the answer from the answer schedule, but by all means you may round that appropriately. And this question is a merit question in total, and the achieved question comes from the probability of female for one of the groups. So just one, either one of these worked out would be an achieved. C part 2 is now looking at the fact that all other groups had 52% of them were male. So we know and this branch 4 had 5 years or less, we have 52% of each group are males. So what percentage of the survey group had their license for 5 years or less were males? So we already know that they had 5 years or less, so we're only looking at this part here. So we can eliminate that probability that we were looking at earlier. So we're only looking at this particular portion of the tree. So what percentage of the group had their license for 5 years or less were males who passed the theory test? Only the theory test. So only the theory test is this branch in here. And we know from our earlier information that this is 30%, 0.3. So therefore, 0.3, 52% of them were male, 0.52. So multiply that by 0.52, and we have 0.156. We are asked what percentage, so just make sure that you put that as a percentage as well. And our marks come from, just let me see, this is a total of an excellence mark. The reason it's an excellence mark is because you are eliminating one of these branches here. And the merit comes from evidence of selecting the restricted branch on the tree. So trying to identify the specific branch that we're looking at. It's actually quite a hard one to place for your merit, but basically identifying it from the tree would help. So that would be your merit. Or if you had the previous probability calculated in there as well, I would imagine that would be merit as well. Alright, so part D is asking us information about another event happening. So far we've got our events as being having license for 5 years or more, having license for more than 5 years, having license for less than 5 years, so more than 5 or less, and then pass the test, pass both tests, pass practical, pass theory, failed both, and likewise pass all tests, pass practical test, pass theory test. So this is all tests. And then it's saying it is found that 13% of those who passed all tests have had such an accident. So then we could say have had an accident and were the driver. So I'll just put DR for driver. 13% of all who passed both tests were the driver of an accident, and likewise down here passed 13%. So we're saying of all people who, so both drivers for 5 years or more, greater than 5 years or 5 years or less, all drivers who passed both tests, 13% of them were a driver and had an accident. Okay, so then we're asked about, there were 500 people who took part in the survey in total, and we know that 8 of them who had their license for less than 5 years passed both tests and had a road accident. So what we're saying is this 13%, does this data suggest that the drivers who had their driver's license for less than 5 years are more likely to have a road accident when they are the driver? So is this 13%, or should we actually have two different percentages for the two different situations, greater than 5 years or 5 years or less? So we need to figure this out by analysing what we've got. So we know that currently we've got our probability. So really I'm just looking at the bottom half of the tree here, and I've got 0.12 there, 0.52 there, and 0.13. So what we're expecting is for this to be 8. Is that right? Yeah, 8. So going back to this, we had 500 drivers, 500 people who took part in the survey in total. We know that the number of those 500 who had their license for 5 years or less and passed both of their tests was 0.12 times 0.52, and the total, multiply that by the total number of people who were surveyed, is going to give us an answer of 31.2, or 31 people. Just rounding that nicely to 31 people. So 31 people out of the 500 had their driver's license for 5 years or less and passed both practical tests. So just that part of the tree down below. Okay, 31 people were in that group. So we know that 13% of them were drivers of an accident. So 31 people times the 31% gives us 4.04, or 4 people. But we are told from our information up above that 8 of the people who had their driver's license for less than 5 years and passed both tests were road accidents. So we can see that this 4 is twice as much as what we'd expect, as the 8 that were given as the actual. So so then we could say that, so what does this data suggest that drives, so yes, so drivers who had their license for less than 5 years or 5 years or less are more likely to have a road accident, etc., etc., and be the driver. Okay, so the 13% might be true for the other group that had their license for more than 5 years, but it is not true for the group that had their license for less than 5 years. So we would expect this to be much larger, this probability here to be much larger than, probably twice as large than 13%. Alright, our marks are given here in total as an excellence grade. If we found the expected numbers, so both of these expected numbers here, we would get a merit grade, and one of those expected numbers, so just either one of them, would be an achieved.